Okay, so welcome to chapter 8. And chapter 8 is an intense chapter. And what we're going to do is we're going to kind of put everything together that we've talked about most this semester in this chapter, in this section. So I want you to pay particular attention to what we're going to talk about today. And this is chapter 8.1. And then, as you know, we're going to be meeting a little bit later on this week to actually go over in person on the meeting chapter 8.2 and 8.3. Again, just because it's not that it's it's a little difficult, but it's also a lot of information that we need to synthesize and put together to help us through this. So what we're going to do today is we're going to talk about something called hypothesis testing. Now, you guys may have heard of the term hypothesis before, and you know from science that a hypothesis, or just from life in general, that anytime you hear the word hypothesis, it means that you're dealing with something that's an educated guess. So within the context of what we're going to talk about today, we're going to talk about, just happened there, we are going to talk about a hypothesis in regards to statistics. What does it mean if we talk about a hypothesis, and what does it mean if we talk about a hypothesis test? So let's start off with this first piece of information here, and let's define what a hypothesis is, again, within the context of statistics. And so a hypothesis within the context of what we're talking about is a claim about a property of a population, mean, standard deviation, or variance, or any of the other statistics that we've been looking at in this class. So it's a claim. It's a claim about a population. It's a claim about a mean. I claim the mean weight of all football players in the NFL is 430 pounds. I claim the population parameter, or I claim that the average amount of people that believe in aliens is 82%. I claim that the average standard deviation for the amount of money that you earn by working in that bank is $243. Whatever it is, it's some kind of claim that you make. And so if we talk about a hypothesis test is a procedure for testing this claim. So if you make a claim, you better back it up. And so when we talk about this idea of hypothesis testing, that's our ability to back up the claim. So again, a hypothesis is some claim that you make about a population, a mean, a standard deviation, a variance, or some of the statistics that we've talked about. And a hypothesis test is a procedure for testing this claim. Okay, well, you claim the average weight of everybody of all the football players in the NFL is 480 pounds, prove it. You know, so that's the kind of challenge that we talk about here, is proving your claim. How do you make sure that what you're saying is honest or true? So as I just said, you can use hypothesis tests to determine if expert claims, it doesn't have to be an expert, it could just be a regular person's claims about some property are correct or incorrect based on some evidence that you've gathered. And I've given you some examples over here, so let's go over some of these examples. And I made these up, but let's take a look at this. One example, police claim that arrest rates have gone down since a new unit began patrolling in a neighborhood. Okay, so let's say, and again, I'm making up these numbers. So this is what the police claimed. The police claimed that the arrest rates, that's P hat, is equal to, or excuse me, P, population proportion of people that arrest, that it's gone down. So let's say the police claim that arrest rates are 18%. You've gathered evidence against, and you've gathered evidence that arrest rates are actually higher. So your P hat is 22%. So let's say you did a simple random sample and you figured out based on your SRS that the arrest rates are actually higher than that. So you can use hypothesis testing. You need some other information we'll talk about in a minute, but you can use hypothesis testing to help you prove or disprove what the police said. Another example, a canned corn company claimed to have 16 ounces of corn in each can, right? So you guys know those cans. Would put on there, they put 16 ounces of whatever in there. You took a simple random sample of 22 cans and actually found that there was only an average of 15.2 ounces of corn in those cans. So you think they're being dishonest. They claim mu is equal to 16 ounces. You found, based on a sample of 22 cans, that the actual mean, or again, based on your sample, that the sample mean was equal to 15.2. Is that enough evidence to tell you that the sample mean based on the fact that your sample mean is significantly less than the population mean that they claim, is that enough evidence to support that this company is being dishonest, that they're not putting enough corn in the ounces of cans that you have there. Another example, a new diet plan claims that if you use their diet, that you'll lose at least 15 pounds on the diet. Okay, so there's a big claim, you will lose 15 pounds. Okay, so you and your friends buy into it. You and 8 of your friends buy into the plan. And so altogether, the 9 of you actually figured out that you lost only 11 pounds when you bought into the claim. So the claim was that the mean was 15 pounds, but when you and your friends actually use this diet, you only lost 9 pounds, which is, again, significantly less than the company's claim, which is 15 pounds. So you can challenge them. But what type of statistical evidence do we have that says that they're correct, right, that their mean is actually correct, or that you're correct, that it's lower than the 15 pounds that they claim? And that's what we're going to do when we talk about hypothesis tests. It's an ability to put together a kind of structural, step-by-step based process to help you prove or disprove that the claims of experts are true. So I thought of a very tongue-in-cheek example of hypothesis testing. I found that this example tends to resonate very well with the students. So what I'm going to do is I'm going to take you through a step-by-step process of hypothesis testing using this tongue-in-cheek example. So again, please know that I completely made this up. It's just fun. It helps people remember how to do hypothesis testing. This is by no means a true statistical test whatsoever. It's just cute, and it'll hopefully help you to remember some of the steps that we're looking at here. So let's say that a pretty bad thing has happened. You suspect that your boyfriend or girlfriend or your significant other is cheating on you. So here's how you would run a hypothesis test on this situation. Okay, so here are 5 steps for you to determine if your significant other is cheating on you or not. So the first thing we're going to do is we're going to start by stating the null hypothesis. And this is a real statistical term here that we're going to use in hypothesis testing. The null hypothesis is always in the form H naught equals some value. Okay, so the null hypothesis is the same thing as saying H0 or your first hypothesis, H naught, N-A-U-G-H-T. And the null hypothesis will always be in the form that H naught is equal to some number. This is what the experts claim. Okay, so if we look at the example above, for this example over here, the experts claim that the mean amount of weight that you lose is 15 pounds. So that would be H naught is equivalent to saying the mean is equal to 15 pounds. Okay, so it's what the other person's claiming. So in this case here, if you go up to your boyfriend or girlfriend, of course, your null hypothesis coming from them is going to be, baby, I'm not a cheater. So your null hypothesis is what the experts claim. And it's, again, it's always going to be in the form H naught equals some value. So here, H naught equals, baby, I'm not a cheater. That's always going to be our first step to hypothesis testing, is you state the null hypothesis. You state what the experts claim. Now, the second step of this is what you believe. So you move on to the alternative hypothesis, also known as H1. In this text, they use H1, but in other texts, they use HA. So they're the same thing, either HA or H1. This is what we call the alternative hypothesis. This is what you suspect or what you believe. Now, the idea is this. This always has to stay the same. Okay, so whatever value, whatever number, whatever words you put here, you have to put them here for the alternative hypothesis as well. But what we are going to do is we're going to switch around the operator over here, this guy in between. So it can come in one of 3 forms. You could either say that you believe that the value is larger than some number. You can say that you believe that the true alternative hypothesis is smaller than some number, or you can say that it's not equal to. We have 3 different values that we can write. In this case, you do believe the person's a cheater. So this is kind of a strange way to say this, but the alternative hypothesis would be, it's not true that baby, I'm not a cheater, which really means the person is a cheater. You wouldn't say they're greater than a cheater or less than a cheater. You would just say they're not a cheater, which means they are cheaters. They are cheaters. Okay, so once again, for those first two steps, you start off with the null hypothesis, and the null hypothesis will always be in the form something is equal to something else. X is equal to 4, mu is equal to 7, sigma is equal to 8. Whatever value that we're hypothesis testing, p is equal to 0.78. The null hypothesis will always be in that form. Now the alternative hypothesis, the H1, these values will all stay the same, except now we're going to use one of the operators based on what we think. Maybe we think the real X value is less than 4. Maybe we think the real mean is greater than 7, right? Maybe we think the real standard deviation is not equal to 8. Maybe we think the real population proportion is, let's say, less than 0.78, but it's whatever we think. So those are the first two steps. Now the third step is, how certain do you want to be that this person is a cheater before you dump their ass? So do you want to be 99% sure that they're a cheater? Do you want to be 95% sure that they're a cheater? Do you want to be 90% sure? Well, if you're 90% sure they are a cheater, remember there's a 10% chance that you're wrong. And that's where those levels of alpha come in. So if you see that we have an alpha level of 0.10, we're allowing for this as being, and one way for you to think about it, and this is not a true statistical way, but it's just a way for you to wrap your brain around it, we're allowing for that to be 10% error. 95% we're allowing there, if you want to be 95% confident that this person is a cheater before you dump them, that means you're allowing for 5% error. If you want to be 99% confident, then that means we're allowing for 1% error. And it's the same alpha that we talked about when we were looking at confidence intervals. Okay, so you have your null hypothesis. You have your alternative hypothesis. And then you determine how certain you want to be. Now we'll tell you what we want your level of alpha to be. So we'll say use a hypothesis test with alpha is equal to 10%, right? And a hypothesis test with alpha is equal to 10% means we want to be 90% certain that this person is cheating before we dump them. An alpha level of 0.05 means we want to be 95% sure. An alpha level of 0.01 means we want to be 99% sure. Okay, so step 1, we're okay with null hypothesis, and we're going to talk more about that in a few minutes. Step 2, the alternative hypothesis. Step 3, the level, how confident do we want to be, or what's our level of alpha? Okay, and now comes step 4. Here comes the fun part. We're going to gather evidence. So we figured out what the null and alternative hypothesis is, and now we're going to gather evidence. Well, if we're trying to figure out if our loved one is cheating, how are we going to gather evidence? I mean, I know this probably makes me look old because I don't think people use Facebook as much anymore, except for people in my age group. But you'd look at their Facebook posts, you'd look at Snapchat, you'd look at their wallet, you'd look at receipts, you'd look at their phone calls and see what type of phone calls were made. You'd interview friends, whatever it is. Different people are going to have different forms of evidence that they want to gather to help them prove if baby is cheating or not. Okay, now, obviously when we run a statistical test, this is not what we're going to do. We're not going to go on Facebook, Snapchat, wallet, you know, all these things. We're actually going to use the p-value. Ooh, p should look familiar. We talked about p's before, and we're going to come back to this in a few minutes in terms of how we can use the p-value to determine if your loved one is cheating or not. But again, in the case of, a p-value to determine if you would either believe H0 or believe H1. But again, in the case of this example, because it's tongue-in-cheek, we're just going to talk about gathering evidence in these examples. Okay, so you did the following. You have your null hypothesis, you have an alternative hypothesis, you have your level of alpha. And again, your level of alpha tells you how certain you want to be that the person is a cheater before you dump them. So then you gather evidence, and again here it's some tongue-in-cheek stuff, and in statistics for real hypothesis tests, we're going to use something called a p-value. And then we're going to use the evidence, which again in the hypothesis testing is a p-value, but here it's Facebook, Snapchat, wallet, receipts, phone calls made, interview, friends, etc., to make a decision. And here are the one of two decisions that you can make. if you feel like based on your evidence that you were correct, then you reject the null hypothesis and accept the alternative one. Well, let's go back there. Remember that the null hypothesis was, baby, I'm not a cheater. Okay, and the alternative hypothesis is, it's not true, baby, I'm not a cheater. Which is code for baby is a cheater. They really are. So what does this mean? If you feel like based on your evidence that you were correct, then you reject the null hypothesis. So that means you reject the null hypothesis, you reject HO, and you accept the alternative hypothesis, which means, guess what? Your significant other is a cheater. And this is, again, tongue-in-cheek. We kind of say that we reject the hoe. We reject the null hypothesis, or we're rejecting the hoe. So we've proved within a certain amount of, with a certain amount of certainty, right? We can never be 100% positive unless the person fesses up. But we proved that our loved one, our significant other, really is a cheater. So that's one decision that we can make. But what happens if we search through all of these? What happens if we search through Facebook? What happens when we search through Snapchat, while it receives, phone calls made, interview friends, etc.? So this means I don't think I had enough evidence. Okay, so then what we do is we fail to reject the null hypothesis, which means we don't reject this. So what we're really saying is we don't have enough evidence to let the boyfriend or girlfriend off the hook. We looked for evidence. We didn't find anything. So I'm going to fail to reject the null hypothesis, or fail to reject the hoe. So what that means, if you fail to reject the null hypothesis in this case, is you just say, I don't have enough evidence to state that you're a cheater or not. And it's kind of an innocent until proven guilty, right? So this fact that you have to fail to reject the null hypothesis means that we can't say this person is true, and we can't say the person is not true. So what does that mean? You go back and you search for more evidence. And you do this a couple more times until you feel fairly certain that the person that you're with is not a cheater, or you just dump them because you didn't want to deal with them anyway. And why are you doing so much searching if that person isn't a cheater? You probably suspect they really are, but that's something else. So again, remember, the two decisions that we're going to make for the end bit based on the evidence that you have is either you're going to reject the null hypothesis and accept the alternative. So you reject HO, and you accept H1, or that's one decision you could make, or you fail to reject the null hypothesis. You fail to reject the hoe. And again, if you fail to reject the null hypothesis, there's nothing that you can say. You just say, I lack evidence. I fail to reject the null hypothesis. I don't have significant evidence to show that my boyfriend or girlfriend is cheating. And that's the general idea behind the structure for hypothesis testing. So let's break this down into little bits and pieces. I want to make sure that you're comfortable with each one of these parts. Now, this chart that we're looking at, Chapter 8, the 9 steps to hypothesis testing, this is really what we're going to use as a guide to when we go about talking about hypothesis test. And so the first thing that we're going to do, we're going to look at hypothesis testing under 3 cases. We're going to look at hypothesis testing for B, for population, for P, for population proportion. We're going to look at hypothesis test for mu, for the mean. And under the mean, we're going to look at 2 different hypothesis tests there. We're going to break this up into 2 different parts. Do we know S or do we know sigma? Based on that information, we're going to make one of 2 decisions. So the first thing you do when you're reading the question is you say to yourself, okay, is this a hypothesis test on P, or is this a hypothesis test on mu, the mean or the population proportion? If it's a hypothesis test on the mean, do I know the population standard deviation, or do I know the sample standard deviation? And we'll get to that in a few minutes. Okay, step 2 then says identify your null hypothesis. Now your null hypothesis will always be in the form the mean is equal to some number, or the population proportion is equal to some number. Step 3, identify your alternative hypothesis. Alternative hypothesis is the mean is either greater than less than or not equal to that number that you stated, or the population is either greater than, less than, or not equal to that number that you stated. Determine your level of significance, which means how comfortable do you want to be with the decision that you're making. Alpha equals 0.01 means you're 99% comfortable. Alpha equals 0.05 means you're 95% comfortable. Alpha equals 0.10 means you're 90% comfortable. And now number 5 says, use your alternative hypothesis to tell you if your test is right-tailed, left-tailed, or two-tailed. So we're going to talk more about what that means in a second, but the general idea is, if you think the true statistic is greater than the statistic that you were given, then that means it's right-tailed. If you think the true statistic is less than the statistic that was given, then it's left-tailed. It's a left-tailed test. And if you think the true statistic just is not equal to the statistic that you were given, then you say it's two-tailed. And we'll talk more about the implications of that in a few minutes. Now, number 6 is find where your sample statistic lies and use one of, there should be 3 formulas given for proportion, mean, or standard deviation. So we're going to use one of these 3 formulas based on the fact, is it a population proportion? Then we're going to use this. Is it a mean? And do we know the population standard deviation? Then we use this formula. Is it a mean? And do we not know the population standard deviation? Then we're going to use this formula. So one is based on a Z and one is based on a T. It's the same thing that we used when we were looking at confidence intervals. Okay, then we're going to, okay, we can choose between 7 and 8. I'm really going to focus on number 8. Number 7 is a way for us to do it, but I really want to hang out here in number 8, so I'm going to ignore that for now. We're going to talk about what our p-value is. And the p-value, the probability that our statistic occurs, or a smaller or larger value than our statistic occurs. And it's the same p-values that we were doing when we were looking at z-tests before. The probability of an event occurring. And then we interpret the results of our tests. Sorry, let me go back up here to the p-value, I forgot. If our p-value is less than or equal to alpha, then we reject the null hypothesis. If p is greater than alpha, then we fail to reject the null hypothesis. Alpha comes from up here. P comes from the statistic that we find when we run it through one of these tests over here. And then we go to part 9, which is interpret the results of your test. Do you have enough evidence to reject the null and accept the alternative, or do you not have enough evidence to reject the null hypothesis? Okay, are they a cheater? This one, they are a cheater. This one, I didn't find enough evidence to say that they were a cheater. They weren't a cheater. I'm going to go back and search some more. So again, like I said before, I want to kind of break this down for you and make sure that you're comfortable with just the little chunks of this. And then the next time we meet, I have just a bunch of examples, and I'm going to get you set up and make sure that you can follow each one of these steps in those examples. Let's take a look. And again, let's make sure that you're comfortable with the first step of this, which is identifying the null and alternative hypothesis. That first step of it, which is H0, null hypothesis, and alternative, which is H1. Now remember, the null hypothesis is what the experts tell you. The alternative hypothesis is what you think. So let's take a look at this example. A company states the mean salary of their employees is $52,500. You interviewed 12 people that work at the company and found the average salary to be $43,900, so you suspect it's less. So the claim is, the company claims that the mean salary of all their employees is $52,500. This is the null hypothesis. It's what they claim. Now the alternative hypothesis, remember that this number is never going to change for the alternative hypothesis. The only thing that's going to change for the alternative hypothesis is the operator. So it's either going to be greater than, less than, or not equal to. So this bit says, so you suspect it's less. Okay, so we suspect the mean is less than 52,500. This is what it would look like. Okay, we know that it's mu because we're dealing with a mean. We know it's 52,500 because that's their claim. We suspect it's less, so we said that here that we suspect it's less. So this would be the setup for the null and alternative hypothesis for this example. Let's take a look at another example. Luke claims that 77% of people that read his book will be able to save more money, and you don't believe it's true. Okay, so Luke is a guy, he writes a book on how to save money. He's trying to get you to buy his book. right? Because he's trying to get you to figure out how to save money. Luke claims that 77% of people read his book, that 77% of people that read his book will be able to save more money, but you don't believe this is true. First of all, 77%, I hope you can tell that that's a proportion or a percent, so that means we're dealing here with P. So here's what he claims. Luke claims that the proportion of people that read his book that will be able to save more money is 77%, so P is equal to 0.77. Okay, the second part, you don't believe this true. When you say you don't believe it's true, what that means is you just don't think it's 77%. You don't say anything about it being more, you don't say anything about it being less. So that means the alternative hypothesis would be that the population proportion is not equal to 77%. Maybe it's 82%, which is good for Luke. Maybe it's 43%, which is terrible for Luke. But this part here, the alternative hypothesis, you don't believe it's true, just means that it's not actually equal to 77%. Okay, let's do a few more examples to make sure that you're comfortable with the null and alternative hypothesis. A soda company claims that in each can of soda, there's only 3.25 grams of sugar. You measured the sugar content in a simple random sample of 45 cans of soda and found that there was, on average, 4 grams of sugar in those cans. So you suspect there's more. Okay. Let's talk about the mean. Let's talk about the null hypothesis and the alternative hypothesis. So the company claims that there's an average of 3.25, and I didn't say average, I should have said average over here, but I did say it over here. So hopefully you can tell that we're dealing with the mean. Their claim is that it's equal to 3.25. Remember that that initial null hypothesis will always be something is equal to some numerical value. You suspect it's more, right? You took a simple random sample of 45 of those cans and you suspect it's more. So this is what you suspect, that mu is greater than 3.25. Okay, let's take a look at 2 more examples. I just want to give this a little bit more space. Let's see, this next example says the following. According to a poll, 13% of people believe in ghosts. You suspect that it's much more than that. So let's talk about how we could write the null and hypothesis, the null and alternative hypothesis for this one. So according to a poll, 13% of people believe in ghosts. You suspect it's much more than that. Okay, so the null hypothesis, now 13%, it's a P, it's a population proportion or population percent. P is equal to 0.13 would be the null hypothesis. Again, it's always going to be something equals something else, and we're only going to look at 2 cases, either P or mu, but you can run statistical tests on sigma, you can run statistical tests on variance, you can run statistical tests on a lot of things. We're just going to look at these 2 cases. So the null hypothesis is P is equal to 0.13. That's what the poll claims. You suspect it's much more than that. You think it's more than 13%. So the alternative hypothesis going to be the proportion of people that believe it ghosts is more than 13%. Okay, and let's try one last one. Test the claim the majority of patients don't mind waiting for their favorite doctor. Okay, the majority of patients. So we're going to start off with, what do we mean when we say the majority of patients don't mind waiting for the doctor? Well, the cutoff for majority is 50%. Anything that's more than 50% is going to be the majority, right? Anything that's more 51%, 52%, 53%, that's majority. So when we talk about test the claim the majority of patients don't mind waiting for their favorite doctors in the office, the majority means we have to be more than 50%. And again, P because it's a percent or a proportion, and we just know that because we're using the word majority in this example. Okay, and if we don't know what the setup is here, remember it's always going to be something is equal to something else because we use the term majority, we know that the cutoff is 50%. So if I said test to claim that the minority of patients don't mind waiting for their doctors in their favorite doctor's office, then we just would have swapped this around. This would have been the same. This would have been P is less than 0.50. Okay, so this is the initial step in this idea of setting up the null and alternative hypothesis. If you remember up here, we also talked about, after that, we talked about this thing that we called Tailness. And I want to make sure that you understand what we talk about when we talk about tailedness. And I made that word up. I don't think tailedness is a real word, but I just want to make sure you understand the idea behind here. So if your alternative hypothesis is greater than the null, okay, so let me draw a graph. Here's the null hypothesis. This is what the experts claim. You actually believe that the statistic is bigger than it. So it's going to be over here. It's going to be to the right of it. Right? So you think the true statistic is bigger than the statistic that they gave you. Then that means it's what we call a right-tailed test. And it makes sense. Anytime we have a greater than, so when we think the true statistic is actually bigger than the one we were given, it's a right-tailed test. If your alternative hypothesis is less than the null, so again, let's draw this graph. Here is our null hypothesis, and we think the true statistic is smaller than it. That means it's to the left of it. Then that's what we call a left-tailed test. Okay, so right-tailed test is greater than, left-tailed test is less than. If your alternative hypothesis is not equal to the null, okay, so here we go. Here's the null hypothesis. And all I said was, I think the alternative isn't equal to it. That means it could be significantly greater than it or significantly smaller than it. It can go over here or here. That means it's possible that it lies either in the left tail or in the right tail. And we call those a two-tailed test. And we get two-tailed tests when our alternative hypothesis is in the form something is not equal to something else. Again, because we're claiming it could be either to the left or to the right of the null hypothesis. So for this, let's look over examples A through E and make sure that we're comfortable just determining the tailedness of each one of these examples. So let's go over here. Let's go back. So all you need to do to determine what the tailedness of it is you need to look at the null and the alternative hypothesis. So we were given the claim that the mean is equal to 52,000 for the amount that people in this office work. They think it's less, right? They think it's somewhere over here. Well, they're saying it's significantly less. And here we thought it was 43,900, but they think it's to the left of it, so they think it's less. Therefore, this is a left-tailed test. Okay. Luke claims 77% of people that read his book will be able to save money. So here's what Luke claims. You don't believe it's true, so you think it could be bigger or it could be smaller. And in this case, that means it could either be left-tailed or right-tailed, which means it's two-tailed. Okay, let's take a look at C. Soda company claims that in each can of soda, there's only 3.25 grams, blah, blah, blah. You suspect it's more. Okay, so in this example, here's what they claim. You suspect it's more, so you actually, right, you came up with that it's 4, and 4 is bigger than 3.25. So that means this is an example of a right tail. If you look, this kind of looks like it's an arrow pointing to the right. It kind of looks like it's an arrow pointing to the left. So you can use the alternative hypothesis to help you determine if it's right-tailed or left-tailed. Let's finish with these two. According to a poll, 13% of people believe in ghosts. You suspect it's much more than that. So you suspect it's more. You think it's somewhere over here in the right tail, so that's right-tailed. And same thing, if you talk about something that's the majority, that means it's bigger. The majority, the test to claim the majority of patients, so it's more than 50%. So that's also going to be right-tailed. So you use the tailedness to help you to determine where you think the true statistic is, and that will tell you in which tail of the normal curve that you think the statistic lies. So that's for the tailedness bit of it. And let's talk about one or two more things before we move on. Like I said before, the significance level alpha for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. By its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when it's true. So what that means is if we have a 95% level of significance, alpha is equal to 0.05, this means 5% of the time we reject the null hypothesis when it's true. 5% of the time we're going to make a mistake. This is what I said before. So keep an eye on alpha. We will tell you what level we want you to use for alpha when you're running these statistical tests. So 2 more things. I don't know why I said this is the last thing. This is the second to last thing that we need to discuss is the p-value. So in a hypothesis test, the p-value is the probability of getting a value of the test statistic that is at least as extreme as the test statistic obtained from the sample data, assuming the null hypothesis is true. If we have a left-tail test, the p-value is to the left of the test statistic, okay? So if your statistic is, well, let's not talk about that now. If we have a right-tail test, the p-value is the area to the right of the test. Here's your p-value over here. If we have a two-tailed test, the p-value is twice the area in the tail beyond the test statistic. If we have a two-tailed test, the p-value is this and this, kind of what we talked about on top over there. And that's why we talked about tailness, because tailness becomes important once we start figuring out how to calculate what the p-value is. So there's a poem I want you to remember, and the poem says the following: if p, well, hold on for the poem. I'll do the poem in a second. But here's 2 things that we need to remember when we're trying to determine what type of decision that we should make on our hypothesis testing. If our p-value is less than or equal to alpha, we reject the null hypothesis. If our p-value is greater than alpha, then we fail to reject the null hypothesis. Okay, so let's go back up to here and let's describe what that means. Let's say that alpha is in, let's say that we're dealing with alphas of 5%, okay? No, I don't want to go there. I don't want to go there. Let's not do that now. We'll do that a little later. Sorry. We'll talk about how to embed our p-value in alpha in a few minutes. But for now, let's hold on to this. If we're comparing the p-value with alpha, here's what we have to remember. If p is less than or equal to alpha, we ultimately make the decision to reject the null hypothesis. If p is greater than alpha, then we fail to reject the null hypothesis. And the poem I was talking about before says the following: if p is low, the null must go. If p is high, the null must fly. Okay, so if p is low, then we reject the null hypothesis. So we cross it out and we reject it. If p is high, then the null must fly. So if p is high, then we fail to reject the null hypothesis. Okay, so let's talk about what this means. I'll tell you what I'll do. I'll sketch a picture over here for you to make sure that you understand what's going on. So for this, if you have a p-value of 0.071 and an alpha value of 0.01, will you reject or will you fail to reject the null hypothesis? Now let's compare them. If we're going to compare p and alpha in this example, think about it in terms of money if you're not good with decimals. Our p-value is like 7 cents and our alpha value is 1 cent. So I hope you can see here that p is greater than alpha. Right? P is greater than alpha, then we fail to reject the null hypothesis. And I want you to understand why. Let's say we're dealing with a left-tailed test here. We have an alpha level of 0.01. What that means is if our statistic, if our p-value is somewhere in this left tail of 1%, that means it's significantly far away enough from the actual mean that we were given. And that means that we can reject the null hypothesis. But if you take a look at this, embedded in the lower 1% of the tail, 0.071 is not located in there. This would be anything that's 0.01 or smaller. That's the way for us to think about these. So we would fail to reject the null hypothesis. And again, I'm going to draw you a picture to try to give you a better understanding. If you don't like that picture, you can ignore it. You can really just remember these two rules here, or the poem: if P is low, the null must go. If P is high, the null must fly. Let's take a look at this example. You have a p-value of 0.0001 with alpha is equal to 0.05. Okay, so you're comparing 5 cents with something that's smaller than 1 cent. And I hope you can see here in this case that alpha is much bigger than p. Okay, so this is an alpha of 0.05. So this is the lower 5% of the tail. And again, we're just going to pretend that all of these are left tail tests. Okay, is it true that our p-value is embedded in this critical region? Is it sufficiently far away enough from the mean or the proportion, whatever it is that we were given? Well, yes, 0.0001 is located in here. So that means, again, that alpha is greater than p, and we would reject the null hypothesis and accept the alternative. Okay, one more example. You have a p-value of 0.01 with alpha is equal to 0.10. So again, in comparing these, when we compare p and alpha, our alpha, we want our statistic to be in the lower 10% of the curve. So here's the lower 10%. And again, it could just as well be a right-handed test, or excuse me, a right-tail test or a two-tail test. I'm just using left-tail because it's easier to visualize here. You have a p-value of 1% with alpha is equal to 10%. So here's our 10%. P-value of 1%. Right, 1% is smaller than 10%, so it's definitely located in this curve, which means that alpha is greater than p. So again, we would reject the null hypothesis, reject the null, and accept the alternative. So we're almost done here. I just wanted to end this with, let's make sure that you're comfortable finding that p-value that we've been talking about. So we're going to take a look at 2 more examples. And again, this is an introduction to hypothesis testing. We are going to spend all that next class taking a look at tons and tons of examples and making sure that you're okay with that 9-step process that we just talked about. So all I'm doing right now is I'm giving you puzzle pieces. You need to kind of understand the puzzle pieces, and then we're going to put the puzzle pieces together and actually look at the puzzle during our next class. Okay, so example. A company states the mean salary of their employees is $52,500. You interviewed 12 people that work at the company and found the average salary to be $43,900, so you suspect it's less. If sigma is equal to 2,300 for the salaries of the company, find P. So find the probability that that statistic occurs. So first of all, I hope you can see here that we're dealing with a mean, and this is the same example that we were looking at before. So the claim is that the mean is equal to 52,500. That's the null hypothesis. We think it's less, so because we gathered evidence that it's 43,900. Now, we're not saying it's 43,900. What we're saying is we think it's less because our sample told us that it was 43,900, and that's less than 52,500. And we know, according to this, that this is a left tail test. Right? So we think the true statistic lies to the left of the statistic that we were given. Okay, so I'm not going to say anything about alpha because I don't want you to compare alpha and p. All I want us to be able to do is just to find p. And here's how we're going to find p. We're going to use, I hope I'm not making you nauseous, we're going to use this. When we talk about find where your sample statistic lies, and then find your p-value, we're going to use this to help us with it. Now, we're dealing with a mean, and in this mean, we know sigma. So this is the formula that we're going to use. Z is equal to x bar minus sigma, excuse me, x bar minus mu over sigma divided by the square root of n. So Z is equal to x bar minus mu over sigma divided by the square root of n. And remember before when we said we convert x's to z's to p's, here we're just going to convert z's to p's. So we're going to do this, we're going to ignore that step. So we're going to convert from z's to p's. Okay, so to convert from z's to p's, let's first convert to z, and you will need your Z chart, and you will need your student's T chart for this as well, but let's do Z's first. Okay, X bar is the sample mean. Our sample mean, I'm sorry, this is incorrect. I don't feel like stopping this video and doing it again. I hope you realize that that actually should have been the mean is less than 52,500. And again, we use that because we just said over here you suspected less. Remember, these numbers always have to be the same. Sorry, it's 10 o'clock at night. I'm a little tired. So when we go to plug this in, we have X bar, which is our sample mean, and our sample mean was 43,900. Minus their claim, which is the population mean, which was, so X bar minus mu, which was 52,500, divided by sigma, which is 2,300, over the square root of n, and you interview 12 people, so it's the square root of 12. So we're going to use RZ then to help us find P. So on my calculator, I'm going to do 43,900 minus 52,500, and then I get negative 8,600. I'm going to divide that by 2,300 divided by the square root of 12, and I get negative 12.95. This information tells us, this tells us something very important. This information tells us that our statistic is 12.95, let me make sure I round it correctly. Yeah, 12.95 standard deviations away from the mean. So our statistic is really far away from the mean. So it looks like, and when we say really far, it's 12, almost 13 standard deviations away from the mean to the left. So our sample is really small. This salary of 43,900 is very far removed from the salary of what the company claims, which is 52,500. Now, remember from here, we're going to convert our Z's to P's. And because we have a left-tailed test, we want to figure out, right? It's a left-tailed test. We think the statistic is over here. When we go to open up our Z chart, give me 1 second. I'm going to try to open up my Z table over here. Let me try to share that with you guys. Share. Here we go. New share. Okay. If you take a look over here, that the smallest value that Z runs is negative 3.49. And when we're at negative 3.49, we have a probability of that occurring as being 0.0002. So anything smaller than negative 3.5, any value that's smaller than negative 3.5 is going to give us a probability of occurring of 0.0001. And sorry, let me switch back. So because it is a left tail test, we don't have to subtract it from 1. If it's a right tail test, we would have to subtract it from 1. So this is a left tail test, so that means our p-value is 0.0001. So the probability of our event occurring is very, 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 very small. That means it probably didn't happen by chance. That means that they're lying. But again, we're going to talk about how to determine if somebody's lying or not. But again, based on what our alpha level is, that's when you make the decision, do you reject the null hypothesis or do you fail to reject the null hypothesis? Now, if you reject the null hypothesis, you have to accept the alternative. But again, we're not going to worry about that until next class. Let's try one more example. Luke wrote a book on how to save money. In this book, he claims 77% of people that read his book and use his methods will be able to save more money. You interviewed 112 people and found that 80 people save money using his methods, so you don't believe Luke is being honest. Let's find P. So again, I'm just going to take you through the first few steps of hypothesis testing. Now, we're dealing with 77%, so that means we're dealing with proportion. So the null hypothesis is that P is equal to 77%. Now, we said we don't believe Luke is being honest, so we just think it's something different from 77%. We didn't say it's more, we didn't say it's less. All we did is we said that it's different from 77%. So this is a two-tailed test. Okay, now it's a two-tailed test because here's Luke right here at 77%. We just think it's somewhere over here or somewhere over here. We didn't say which one. So it could be in either tail, so we call that a two-tail test. So which statistic are we going to use to help us figure out P? Well, again, let's go back up here. For proportion, we have this statistic over here, which tells us P hat minus P divided by the square root of PQ over N is equal to Z. So we're going to take Z's and convert that to P's. I'm going to have to go back to that formula in a second because I already forgot what it was. Z is equal to, hold on, let me just see if I can cut and paste that guy. Oops. Hold on one second. Oh yeah, I can do that. Let me copy you, buddy. And let's bring you back down here and let's paste you in. Where are you? Okay, you can paste it over there. I don't care where. Seriously. P hat minus P over the square root of PQ over N. P hat minus P over the square root of PQ over N. Okay, so here's how we find our Z value. And again, what we're going to do is we're going to take this Z value and we're going to convert it to our P value. P hat is our sample statistic. Now, we are going to figure out what our sample statistic is. And here it says, you interviewed 112 people and found 80 people save money using his methods. So what does 80 over 112 look like as a decimal or as a proportion? 80 divided by 112 is the same thing as saying 0.714. So our P hat is 0.714. Okay, that's our statistic. And again, we got it from this piece of information over here. Minus P was his claim, minus 0.77, divided by the square root of P times Q divided by N. Now P, right here, that's the population proportion, which is his claim, which is 77%. Remember that Q is 1 minus 77%, so that's going to be 23%. N is the amount of people we used in our sample, and it's 112. Okay, so Z is equal to 0.714 minus 0.77, which equals, so in our numerator, we're going to get negative 0.056 divided by, I'm going to do this all on my calculator, I'm going to try to, 0.77 times 0.23, divide that by 112, and I get 0.00158,125. Okay, 1, 2, 3, yeah, 0.00158,125. And so when I divide the two, negative 0.056, I'm going to divide that by the square root of 0.00158,125. And I get negative 1.41. So that tells us that our statistic, based on our sample size, our statistic is 1.41 standard deviations to the left of the mean. Okay, so this is him. Our statistic is over here. So what we want to ask ourselves is, again, when we're determining if we're going to reject the null hypothesis or accept it, is are we deeply enough embedded in here? But we're not done. This is our Z value. Our Z value is negative 1.41. Because our statistic is actually to the left, even though it's two-tailed, our statistic truly is to the left. That means we don't have to worry about subtracting the area from anything else. So I'm going to switch back over here to my Z table. Okay, Z equals negative 1.41. Here is negative 1.41 for that Z value. We get 0.0793. So 0.0793. Okay, but we're not done because we're dealing with a two-tailed test. Let me go back up here and show you guys real quickly. If we have a two-tailed test, the p-value is twice the area in the tail beyond the test statistic. So that means only for two-tailed tests is this going to work. Anytime we have a two-tailed test, we're going to take our p-value and multiply it by 2. Because what we're saying here is that our statistic can be in this tail or in this tail. So it can be this plus this, which means we're going to double this area. So we're going to multiply that value by 2. So p is equal to 2 times 0.0793, and we get 0.1586. So I'm going to end right here for an introduction. This is chapter 1. And again, I want to stress that it's okay if you don't 100% understand all of these topics right now. All I'm doing right now is I'm just laying out all the puzzle pieces on the table. What we're going to do when we meet next time is we're going to put all these puzzle pieces together and we're going to look at what the big picture looks like. So just make sure the few things that I really want to make sure that you're comfortable with is make sure that you can figure out what the null and alternative hypothesis are. Make sure that you can tell the tailedness of the test, right-tailed, left-tailed, two-tailed, and then make sure you're comfortable with this bit too, this idea of comparing our statistic with alpha, right? And keep in mind this poem, if the p is low, the null must go. If the p is high, the null must fly. Okay, thank you very much, and I will see you guys in a few days.